Great, now we're going to do problem number 32 here, and we want to solve the system of equations by putting it into reduced row echelon form. So first things first, let's turn this into a matrix. Just using in this augmented matrix, the first three columns are the coefficients and the last column are the solutions, right? So this is an augmented matrix. So to get to reduced row echelon form, I'm going to first aim to get some zeros right here. And so I'm going to change colors. I'm going to leave the top row exactly as it is. I'm going to do for the middle row, because I like to not get fractions, I'm going to, instead of cutting things in half, I'm going to double the first row and subtract from that the second row. So that would give me a 0, 3, 3, and a 0. Likewise, I'm going to quadruple the first row and subtract from that the third row. So in this case, I would have a 0, 3, so 4 minus 1. And then 8 minus 5 is also a 3 and a 0. Great, things are starting to look a little bit nicer, although there is something here that you might learn to recognize that's going to be weird. The fact that the last two rows are actually the same, that's a big warning sign, because when I try to get a 0 right here, something strange is going to happen. So I'm going to rewrite the first row as it is, rewrite the second row as it is. And then if I try to get a 0 right here by, say, row 2 minus row 3, I will have a row of all zeros, which means that these equations aren't actually enough to determine my shape. It's a little strange, but another way of saying that is when you have a graphical representation of this, of three planes, where do they intersect? They're not intersecting on one point, because two of these equations is actually enough to explain this whole situation. Now, how do I write my final solution? What you could do, which is a fine thing to think about, I might simplify this a little bit still. I might, for the sake of this example, I'm going to simplify the middle row now by dividing it by 3, so a third of that middle row. So I get a 1, a 1, and a 0. And then I might even, thinking about this situation, I might use that middle row to simplify the top row even. So if I want to get all the way down to something really nice, I can think about taking that first row and subtracting off that second row, which will give me a 1, 0, 1, 0. And this is a fine sort of place to finish. Now let's interpret this. If I were to turn this back into equations, let me zoom out a tad, back into equations of x, y, and z, right, kind of like we had before, this would give me that x plus z is equal to 0, and then y plus z is equal to 0. And that's it. The bottom row just says 0 is equal to 0, which is true, but it's not very helpful. So the way we can sort of finish this off is you can actually consider z as being this sort of a free variable. So then how do we express our solution? Well, one way that you might express a solution here, if you've done it sort of in an algebra class, is you might just say, well, z is an arbitrary variable, z is a free variable. You might say x is equal to negative z, though. Y is equal to negative z. And z is just equal to itself. That's one way you might sort of think about expressing it. Another way, if you had to do it as a sort of an ordered triple, you might just consider it negative z, and z. Or what you might also call it, x, negative x, something like that. Now, what we might see our book do, trying to give us something that's a little bit more vectory, you might say, for instance, is you might think, well, I could find a parametric equation that would explain this as well. I could say, for instance, that there is a particular solution, right? If z was 0, I know a particular solution for this, which you might express in your book's notation. It could be a vector that's just x, y, and z could all be 0. That's a solution. You could also do, hey, I could do 1, 1, and -1. That's a solution. Any particular solution will do for the way your book would express it. So I'm just going to use the zeros because that's the simplest. And then if we want to do a homogeneous solution as well, what we'll often do is call z, right, that free variable, by some parameter's name. So often t, r, or s are used. And so you might think of it as, well, if this was t, then you'd have negative t and negative t. But that's a little clunky when I could just write it as t times the vector -1, -1, 0. And that right there is sort of how your book will more typically write it. So a way you might sort of finish this off, let me zoom out just a tad so I can put it all on the same screen, is let's finish it off in maybe a blue color, is this bit of a set theory notation, which you might see in your book. So you say, well, our solution is going to be the set of all, vectors with 3 components, such that, your initial system is satisfied with what that indicates. And the way we can express this is with our t times, well, maybe I should, to be extra clear what's going on, is I would do my particular plus my homogeneous solution here. But for us, that 0 is sort of irrelevant, right? So I'm just going to not worry about drawing that just to make it look a little bit nicer. So we're going to have the t, -1, -1, 0. Such that t is in R. Right, so t is a real number. And there's a fine solution. If you wanted to go above and beyond, you might recognize that, well, this line, since it's parameterized now, is actually equivalent to the one with the positive ones there. So that would also be a solution. It would just be parameterized a little bit differently, which is okay. I'm just going to leave it like this for the sake of this example.